Today we've got another organic identity question. So if we look at this question, we haven't got much really. We've just got the mass spectrum. They've given us an NMR and luckily they've told us it's an ester. So we've got something to work with there. We know that the ester group is C double bond O, C single bond O. So the first thing we're going to recap is the principle of NMR, which is the number of peaks is equal to the number of unique hydrogen environments. The second one is the area, formerly known as the integration, so the integration value is equal to the number of hydrogens in the environment. And then number three, which is more of a general one, the greater the electronegativity leads to a greater chemical shift. So what I mean by that is when you have a hydrogen environment that's surrounded by electronegative atoms like oxygen or fluorine and so on, it drives the chemical shift to the left. Remember, the scale on NMR goes backwards from right to left. Okay, so with that said, we have the integration numbers. They are the ones given to us in red. So for example, that one there, there's 3 hydrogens in the environment. And we have obviously the number of peaks, which we can see. So I can immediately see from my spectra, number of peaks is 4. So therefore, there are 4, proton by the way means hydrogen environments. Now I'm going to turn to my NMR table to dig a little deeper to see what those environments could be. Right? Whenever you see a peak at 7, this is a really strong clue. It's always the same molecule, which is benzene. So that's a really nice start. So we know that there's going to be benzene there because if you look at the NMR spectra, that's the only thing that appears in that range and goes some way to explaining why the MR is 164. So remember, the molecular ion peak on a mass spec graph is the last peak in the graph, in the spectra rather, and indicates the mass of the molecule, which in this case is 164. I also know that in a benzene ring there's 6 hydrogens, but this one is only showing 5. So there's only 5 hydrogens in that environment, which means one of the places where hydrogen would be on the benzene ring is substituted with something. So there's something coming off the benzene ring. Now let's turn our attention to the other peaks. Now that one there, right, you can see that's about 4.4, 4.5. So quite the chemical shift. So hydrogen bonded to a carbon, which is directly attached to an oxygen. So this bit, and there's 2 hydrogens on the environment. So it could possibly be a CH2. And then it's also split, if you see it's split into a triplet, means it must be next to a carbon which also has 2 hydrogens, okay? Because the splitting is caused by the number of hydrogens on the adjacent carbon. And the split is determined by the n+1 rule. So if the number of hydrogens on the adjacent carbon is 2, then 2 + 1 will make 3, which gives a triplet. Now the same can be said for this one, look. So we have 2 hydrogens in that environment, and that's at about 2.9, 2.8, 2.9. So again, that could be something with a CH2 attached. So if you look at the spectra, possibly to a C double bond O. So that fits nicely for the C double bond O with maybe a CH2. And then finally, we have this peak there, which is a singlet, which means the environment is attached to a carbon with no other hydrogens on it and has an integration of 3. So whenever you see an integration of 3, it's always going to, with the most of the time, will be a CH3. And that's at about 2.2, 2.3, which again, if you look at the data table for the NMR, the only thing that fits that would be a hydrogen bonded to a carbon, which is directly attached to a C double bond O. So now let's put the pieces down below and see what we have. So we have the benzene ring, we have this bit, we have possibly this bit, and we know it's got to be an ester. So remember what I said in the previous video, just put the pieces down on the page like pieces of a jigsaw and then work out how they could fit together to meet the criteria of the NMR spectra, which is 4 unique peaks. So we know one of the peaks is going to be due to the benzene and the other 3 are going to come from the other parts. Let's go ahead and try and put that together. So we put the benzene ring like so. The only way to get 2 triplets is a CH2 next to another CH2 because, as I said, 2 + 1 would make 3 for the triplet. So we could have maybe carbon there and then another one there. And then that's attached to the So C double bond O. But we run into a problem here now because we need to see if this actually works. So we've got, on my proposed drawing there, I've got a CH3 attached to an oxygen. So that would give a singlet. But for that to be shown in the NMR spectra, I would have to see a singlet with an integration of 3. There is something in that range, but it's only got an integration of 2. So we know that this structure cannot be correct because we'd expect it to be a singlet with 3H or just 3, but there isn't a singlet at 4.2, 4.3. It's got a 2 instead. So that can't be right. So let's try again. So by this process of elimination, I'm teaching you how to sort of think through a problem, because you're not always going to get to the answer immediately. So let's go back to the benzene ring. So now let's think about how can I turn this around to get this part in, which is what I originally proposed, which is a CH2 attached to an oxygen. So maybe this time we've got to have that with the oxygen there, C double bond O there, and then put the CH3 that side. Now, that peak there fits this bit perfectly. So that's looking promising. We got the CH2 directly attached to the oxygen. So that, when I put a tick there, is that part there, which means the only thing we have to put in now is the other CH2, and then that must attach to the benzene. So let's do a quick check. Does this actually work? So the proton environments are, I will circle them in blue. The benzene ring, the blue one, let's call that A, which is going to be that peak there. We have a CH2 attached to a benzene to the left and a CH2 to the right. So let's call that B. And that would be a triplet. So that one is going to be there. So that's B. Then the other CH2, C must be that one. So how did I know the C is the one is the triplet to the left and not to the right? It's because of the chemical shift. It's attached directly to an oxygen. So remember what rule 3 says. The greater the electronegativity, the greater the chemical shift. So that's C, which means the CH3 attached to the C double bond O. This one, it's got to be that one. So that's D. So that is a molecule, but we need to do one final check. We were told that the MR is 164. So does this add up to 164? So benzene has 6 carbons, so 6 times 12 is 72, plus its 5 hydrogens would be 77, plus 2 CH2s, which is 14, plus another 14, just calculating this as we go along, plus an oxygen, 16, plus a C double bond O, which is 12, plus another 16, and then finally CH3 in the end, which is 15, gives exactly 164. So we know that the MR fits the proposed molecule I've drawn. So that's a second confirmation that this molecule is correct. Right, I appreciate these questions are difficult. Don't worry, they're meant to be difficult. So if you have any questions, please comment down below and I will get back to help you. And yeah, like and subscribe if you've had any value from this. And I look forward to seeing you in the next one.